To briefly review, the major portions of the Apollo spacecraft are the launch escape subsystem, the boost protective cover, the command module, the service module, and the spacecraft adapter, which carries the LEM, or Lunar Excursion Module. During the current reporting period, development and manufacturing efforts were evident in all areas of Apollo spacecraft activity. In subsystems development, for example, work continued toward early manned flight qualification. Such efforts were seen in environmental control subsystem development. North American Aviation, Downey, California, conducted the first manned ECS breadboard tests in a command module test cell. The tests included ground-level subsystem checkouts and hooking the space-suited test subjects into the simulated spacecraft suit ventilating circuits. ECS equipment is produced by the Air Research Division of the Garrett Corporation, Los Angeles. Another major spacecraft subsystem is that for guidance and navigation. The prime subsystem contractor, AC Electronics, Milwaukee, delivered all Block 1 G and N subsystems to North American and began Block 1 qualification testing. Block 1 spacecraft will be used for Earth orbital flights. Block 2 spacecraft will be used for lunar missions. Interrelated with spacecraft guidance is the stabilization and control function. Block 1 stabilization and control subsystem tests were conducted by the subcontractor Honeywell Corporation, Minneapolis, Minnesota. The stabilization and control equipment includes the translational hand controller, the flight director attitude indicator, and the rate gyro assembly. As of March 1966, Honeywell had completed Block 1 qualification testing and had delivered the majority of Block 1 subsystems. Another function vital to guidance and control is the spacecraft's reaction control subsystem. North American completed RCS breadboard duty cycle tests in support of the first and second unmanned Apollo missions. Tests are continuing to qualify the Rocketdyne-developed RCS equipment for manned Apollo flight. Block 1 qualification testing of the service module RCS engines was started in the fall of 1965 by the subcontractor Marquardt Corporation, Van Nuys, California. Subsystem duty cycling tests with the engines mounted in an operational quad configuration were completed at Downey in support of the 009 and 011 spacecraft missions. The service module RCS engines are similar to those used in the command module. Both are fueled with hypergolic propellants and are controllable from a maximum one-time burn of 500 seconds to a large number of pulse firings as short as 20 milliseconds. The second and largest propulsion system carried by the spacecraft is the service propulsion subsystem. With the attached nozzle extension, the service propulsion engine measures over 12 feet tall. Aerojet General, Sacramento, California, is the manufacturer. The first flight model SPS engine was installed in the 009 service module in October 1965. The engine uses pressure-fed hypergolic propellants and is capable of multiple restarts. Altitude testing of the service propulsion engine is being conducted at the Air Force's Arnold Engineering Development Center, Tullahoma, Tennessee. On 2 occasions, the thrust chamber failed during developmental firings. The problems were corrected and the engine successfully completed Block 1 qualification tests in April 1966. Service propulsion subsystem plumbing tests were concurrently run at NASA's White Sands Test Facility, New Mexico. Test programs were completed in support of the 009 and 011 spacecraft missions. A nozzle inertia simulator is used for the firing tests. Titanium fuel and oxidizer tanks for the service propulsion subsystem are built by the Allison Division of General Motors, Indianapolis, Indiana. During early subsystems testing, nitrogen tetroxide, used as a propellant oxidizer, attacked the titanium, causing severe corrosion and structural failure. The problem was overcome by adding a corrosion-inhibiting chemical compound to the oxidizer. The compound did not degrade the oxidizer's thrust characteristics. Voice, data, and television links between the spacecraft and Earth will be handled by the communications subsystem, which is the subcontract responsibility of Collins Radio, Cedar Rapids, Iowa. Collins delivered all Block 1 communications equipment and had started manned flight qualification testing. Electrical power for the spacecraft will be supplied by 3 fuel cells carried in the service module. North American installed 3 operational fuel cells in Apollo House Spacecraft number 1, marking the first installation of fuel cells in Apollo spacecraft hardware. The cells will aid subsystems interface and performance checks in the static development spacecraft. Fuel cell endurance tests conducted at the Manned Spacecraft Center and by the subcontractor Pratt & Whitney, East Hartford, Connecticut, have produced sustained operating records of over 1,000 hours, more than double the life test requirements. In the event of a pad or early launch emergency, the command module will be pulled to safety by the launch escape subsystem. The legs of the launch escape tower are attached to the boost protective cover. The cover is a lightweight cork and fiberglass shield which protects the command module during boost flight. It is removed with the jettisoning of the launch escape tower. The cover prevents sooting of the command module windows during tower jettison and helps regulate cabin temperatures during the frictional heating of boost flight. Testing of the launch escape subsystem continued at the Army's White Sands Missile Range, New Mexico. On May 19, 1965, unmanned Command Module Boilerplate 22 was launched in a high-altitude abort test. 5 seconds after liftoff, the Little Joe 2 launch vehicle began an unprogrammed roll. The roll rate increased, producing a realistic launch emergency and automatically triggering the launch escape subsystem. The launch escape subsystem performed perfectly under conditions which far exceeded the limitations of Saturn V emergency detection equipment. While not all mission objectives were attained, missing data were gathered on later subsystem tests. On June 29, 1965, a pad abort test of the launch escape subsystem was conducted using unmanned Command Module Boilerplate 23A. Primary objectives of the test were to observe the performance of the boost protective cover and to determine the ability of a canard turnaround system to orient the module blunt end forward, the best position for parachute deployment. All mission objectives were achieved. On January 20th, 1966, the first flight article Apollo spacecraft, Command Module 002, was launched from White Sands in a power-on tumbling abort test of the launch escape subsystem. Nearing abort altitude, the Little Joe 2 was directed to execute a pitch-up maneuver which imposed the most severe dynamic stresses anticipated for Apollo. The launch escape motor then ignited and sped the command module free of the launch vehicle. The canards deployed on schedule and oriented the command module blunt end forward. All subsystems performed as programmed, including cutting of the parachute risers at impact. The test qualified the launch escape subsystem for all manned Apollo flights. The command module's parachutes are part of the Earth landing subsystem, which includes drogue and pilot parachutes and their deployment mortars, and 3 main 85-foot ring sail parachutes. Parachute drop tests are being conducted by the subsystem contractor Northrop Ventura at the Navy's El Centro, California test facility. A modified C-133 aircraft is used for the tests. The last of 12 Block 1 qualification drop tests was conducted in February 1966. Block 2 qualification testing is scheduled to start in mid-1966. This is a mock-up of a Block 2 command module. Note the distinguishing docking probe. The hatch and probe hardware will be removed to permit transfer of the LEM flight crew prior to a lunar descent. During development verification tests at North American, test subjects practiced removing and storing the crew tunnel hatches and docking hardware. Re-entry heat protection for the command module will be provided by the heat shield, which forms the module's outer surface. The ablation surface consists of fiberglass honeycomb sections which are bonded to the module's outer metal shell. The 370,000 honeycomb cells are then individually filled with a phenolic epoxy ablator material. Avco Corporation, Lowell, Massachusetts, is the subcontractor. After curing, the ablation surface is machined to final dimensions. By the end of March 1966, Avco had delivered the heat shields for the first 3 Block 1 spacecraft. Concurrently, North American's Rocketdyne Division completed tests of heat shield temperature sensors. The sensors are placed at the heat shield bond line under the ablation material, where they report re-entry temperatures. A sensor was installed in a section of heat shield structure, and the sample was subjected to a sustained heat blast of over 4,000 degrees Fahrenheit. The sensor remained intact and continued to function after the heat shield structure had disintegrated. Progress in subsystems development was matched by activity in flight article manufacturing. By the fall of 1965, the first Block 1 flight article, Spacecraft 009, had completed subsystems installation and was fitted with its aft heat shield. The spacecraft's modules and launch escape subsystem were then moved to the final checkout area and mated in preparation for acceptance testing and buy-off. Integrated testing was conducted with the second of 3 acceptance checkout equipment stations in operation at Downey. The stations are built by General Electric, Daytona Beach, Florida. They are capable of continually monitoring over 25,000 spacecraft test samples per second. 12 such checkout stations will eventually be in operation at Apollo contractors and NASA sites across the country. Remaining Block 1 spacecraft were in various stages of assembly, subsystems installation, and testing. The modules for Spacecraft 011 for the second unmanned Apollo mission were in final systems installation before entering acceptance testing. The modules were shipped to Cape Kennedy in April 1966. In Block 2 manufacturing, the inner crew compartment section for the first Block 2 command module was in ultrasonic testing. Sound waves are used to determine the quality of the bond between the aluminum honeycomb reinforcing panels and the underlying aluminum shell. Crew compartment sections for Command Module 103, the first spacecraft to be available for a lunar mission, were in chemical degreasing and etching prior to having reinforcing panels bonded. Degreasing assures a continuous bond of the honeycomb reinforcing structures. A final dip in a sulfuric acid solution etches a slight tooth in the metal. This helps assure a permanent grip of the bonding agents. The third major Apollo spacecraft component is the spacecraft LEM adapter. North American manufactures the adapter at its Tulsa, Oklahoma facility. The 29-foot-high adapter is constructed chiefly of aluminum honeycomb sections. Tests were begun at Tulsa to perfect the adapter's panel separation system. In space, the panels will be blown back to permit the extraction of the LEM. Transportation of the first adapter sections from Tulsa to Cape Kennedy was handled by Army helicopters. Adapter number 4 for the O-11 spacecraft was delivered early in 1966. The 22-foot-high Lunar Excursion Module is the fourth major component of the Apollo configuration. It is produced by Grumman Aircraft Engineering Corporation, Bethpage, Long Island. The LEM subsystems parallel those of the command and service modules. They include an environmental control unit, an alignment optical telescope, and various communication and radar antennas. Storage bays in the module's descent stage will hold scientific equipment that will be used during the lunar stay. A collapsible antenna, for example, will be erected and left on the Moon for transmitting scientific data back to Earth. Manufacturing efforts at Grumman were reflected in assembly progress on the first flight-configured ground test article. The module will be retained at Bethpage as a house development spacecraft. The first flight article LEM, scheduled for an unmanned flight aboard the 6th Saturn 1B launch vehicle, was in structural assembly. It was on schedule for delivery to Cape Kennedy in late 1966. Propulsion Ascent Stage Number 2 is destined for hot firing tests at NASA's White Sands Test Facility. The LEM test area at White Sands was completed in early 1965. It contains one ambient pressure stand and two altitude stands. Tests of the facility's steam generating system were begun in February 1966. The equipment successfully produced a simulated altitude of 125,000 feet. The chambers are evacuated by ejecting high-pressure steam past the chamber vents. In January 1965, heavyweight ascent stage test rig number 3 was installed in the ambient pressure stand at White Sands. The rig contains heavyweight tanks, tubing, connections, and fittings for the initial subsystem firing tests. The first firings, using the HA-3 test rig and a Bell Aerosystems ascent engine, took place in April 1965. Altitude tests of the ascent stage propulsion subsystem will begin at the facility in mid-1966. Development altitude firings of the Bell engine were completed at the Air Force's Tullahoma test facility. Qualification testing of the engine began in April 1966. Developmental firings of the LEM descent engine were conducted by TRW at Tullahoma. And at the company's high-altitude test stand, San Juan Capistrano. In support of Apollo development schedules, a number of specialized test facilities have been created. Guidance and navigation equipment is calibrated with the aid of this spacecraft polarity checker. A crew couch vibration tester was used to determine the structural reliability of couch components subjected to launch vibrations. Command module heat shield structures are being subjected to the alternate hot and cold temperature extremes that will be encountered in space in this thermal testing facility. This is a tumbling and cleaning fixture designed to dislodge foreign particles which could become free-floating contaminants during spaceflight. Command Module 006 was used in the demonstration test of the fixture. The outdoor pool at Downey was used for continued structural testing. A boilerplate spacecraft fitted with an aft heat shield structure of the type intended for spacecraft 009 was dropped to determine the structure's ability to withstand the most severe conditions of impact angle and velocity anticipated for Apollo. This is a playback of the drop test photographed by high-speed cameras inside the command module. Failure of the heat shield supporting structure resulted in design changes which were successfully demonstrated in later water drop tests. The pool facility was also used to verify the integrity of other command module structures, such as the crew tunnel and crew compartment. These scenes show the second of two positions in which the module can stabilize itself in the water, either apex up or apex down, as shown here. To invert an apex down spacecraft, a righting bag system was developed by North American. Block 1 testing will be completed by mid-1966. Development work of a different sort was underway in perfecting the designs of Apollo lunar mission spacesuits. Engineering models of the soft suit pressure garment and backpack were delivered by the contractors International Latex, Dover, Delaware for the suit, Hamilton Standard, Windsor Locks, Connecticut for the backpack. The equipment is part of the Apollo Extravehicular Mobility Unit, which includes an extravehicular visor assembly that can be attached to the helmet. The tinted visors can be used singly or in combination. The latest developmental hard suit for Apollo extended lunar surface investigations and possible deep space applications was also demonstrated. The lightweight aluminum and fiberglass assembly was developed by Litton Systems Incorporated, Beverly Hills, California. Apollo goals came closer to operational status with the arrival of the first production Apollo spacecraft at the Kennedy Space Center in October 1965. Following an extensive program of inspections, cleaning, build-up, and testing, the mated command and service modules provided the first view of flight-configured Apollo spacecraft modules. On December 26th, the command and service modules and the attached adapter section were mated to the Saturn 1B Launch Vehicle 201 at Launch Complex 34. Saturn launch vehicle development is under the direction of the Marshall Space Flight Center, Huntsville, Alabama. Throughout January and February of 1966, pre-flight tests were conducted to ensure every possibility of mission success. The unmanned spacecraft was scheduled to be launched on a 5,000-mile ballistic trajectory down the Atlantic Test Range. The mission would also help confirm the all-up concept of flight testing, in which all launch vehicle and spacecraft components will be flown together live for the first time. On launch morning, February 26th, low gaseous control pressures in the launch vehicle forced several recyclings of the countdown and an eventual scrub. However, 10 minutes later, the problem was corrected and the scrub decision was reversed. At 11:12 a.m. Eastern Standard Time, February 26th, Apollo Saturn Mission 201 was on its way. Staging occurred approximately 2.5 minutes after launch. The 200,000-pound thrust second stage engine then ignited and propelled the spacecraft to a 310-mile altitude. This was the separation action recorded by an onboard camera. "40 minutes later, the command module landed approximately 43 nautical miles short of its predicted impact point. Recovery was performed by crews aboard the carrier Boxer. Mission objectives included subjecting the command module's heat shield to a fast re-entry heat buildup. 2 burns of the surface propulsion subsystem accelerated the re-entry speed of the spacecraft so that heat rate buildup approached the values that will be encountered during lunar mission re-entries. Fluctuations in SPS engine firing chamber pressures degraded the entry velocity, resulting in lower surface temperatures than planned. However, data protractions verified that the current heat shield design is able to withstand an atmospheric entry from a lunar mission. The successful completion of the first Apollo Saturn mission was one of the most important accomplishments to date in the development of a manned lunar mission capability. In summary, progress during the reporting period saw Apollo system hardware in manned qualification testing. There were problems, but they were overcome with no distress to overall schedules. Flight article Apollo spacecraft have started to come off the assembly line. And subsystems tests have given way to full-scale flight verification testing. In all levels of Apollo spacecraft activity, program milestones continued to point the way to a scheduled manned lunar landing within this decade.